Hello, today I'll be presenting my project on the designing and performance evaluation of a microgrid for a remote community in Newfoundland. My name is Mohammad Sizan Islam and this project was completed under the guidance of Dr. Mohsin Jamil in Memorial University of Newfoundland. This is my project outline and I'll discuss these points in my project. These are the objectives of my project. The main objective of this project is to find a suitable location in Newfoundland for setting up a microgrid. We aim to design this system using all available energy resources, which is obviously renewable energy sources, and evaluate its performance using Homer Pro software. Additionally, the aim is to select the best combination of renewable sources for optimal performance. We have chosen Nain, which is located in the University region due to its higher population and economic activity compared to Hopedale. Nain offers more opportunities to work with power solution for residential, commercial, and industrial loads. The existing power source in Newfoundland, Nain, Newfoundland, comprises 4 Caterpillar diesel generators. The problem statement. Our primary goals are to identify the best possible combination of PV, wind, and battery storage. We also aim to determine the energy generation patterns over time to understand the seasonal variations. Furthermore, we'll evaluate the microgrid's ability to meet the energy demand, assess its economic feasibility, and calculate the environmental benefits by comparing the reduction of greenhouse gases against the existing diesel power system. This is the design of our system, that how we're gonna implement our microgrid into that. First of all, we need to analyze the load. There are 3 types of load in that selected location, which is commercial, residential, and industrial. And here you can see the figure. This is the seasonal hourly data and yearly load analysis for the commercial sector. This load analysis involves examining the commercial, residential, and industrial loads using the seasonal hourly data. For this project, we consider the maximum peak load, which occurs in December and January. Here, the residential load is up to 100 kilowatt. The commercial load ranges between 550 to 350 kilowatt, and the industrial load ranges from 1000 to 12,000 kilowatt. But our focus will be on the residential and commercial loads for this project. This is the proposed system architecture. The solar PV and battery are connected with the DC bus, which you can clearly see on the right side of the Homer diagram, and the power harness from these 2 sources will be converted into AC by an inverter. And on the left side of the Homer diagram, you can see a diesel generator and wind turbine, which is directly connected to an AC bus. This proposed system includes the following components. The solar panel will be supplied by the Canadian Solar Superpower. The model is CSK295MS, which is 220 kilowatt. The wind turbine will be Zend L33, which is 330 kilowatt. The diesel generator, which is existing in this region, is the Caterpillar genset of 3500 kilowatt. The inverter is supplied by Kewa, and the battery is the BAE Solar 17 PVS 3230, which is 480 kilowatt. Now we'll discuss the component-wise specifications. First of all, the PV panel. The PV panel used is the Canadian Solar Superpower CS6K295MS, originated from China with a power output of 295 watts and an efficiency of 18.02%. The wind turbine is the Zand L33 with a capacity of 330 kilowatt and an efficiency of 46%, which is compatible with grid and generator system. Now let's discuss about the inverter and battery. The inverter is KWKF BCS 500K from France with a capacity of 411 kilowatt and efficiencies of 95%, and the battery comprises a lead acid solar cells from China with a nominal capacity of 5.41 kilowatt and a total of 480 units. Now let's discuss the result and discussion after the simulation. From the figure we can clearly see that the 15% and 85% of the existing diesel power of the location has been replaced by solar power and the wind turbine respectively. The orange part of this graph shows the wind turbine and the blue ones represent the PV. Although there are some major issues of solar power from May to August due to change in weather situation. Let's discuss furthermore. Here the annualized savings will be approximately 470,000 Canadian dollar, whereas the investment was 570,500 CAD, which is the existing system. The project lifetime is considered 25 years. The component-wise cash flow generation will be designed along with the nominal discount, inflation and interest rates, which is 8%, 2% and 5.9% respectively. And the reduction of cost will be almost 25K per year. The data is captured from Homer Pro and will be utilized to construct a 25-year cash flow analysis that will provide a clear picture that what is the economic output of this project. The cost analysis is demonstrated and in the figure where the investment of all components will be utilized. One of the main purposes of using the Homer Pro software in this project is that the software allows option-wise component selection and economic results to select the perfect combination. Likewise, this project will also have some options here. Here in option 1, we can see that the combination of PV panel and wind turbine and a battery storage, like discussed in the previous options, these are like discussed previously, that this option might have a drawback in night time. This option may have a drawback in the night times and cloudy days that will cause the performance of the PV panels, but the presence of a battery storage bank will play a pivotal role. Presence of battery can be at use immediately in terms of emergency, no matter in cloudy days, at night or even in winter days. Option 2 is the combination of the existing diesel genset, PV panel and wind turbine. Here the advantage of this is the less initial cost of PV panel and the wind turbine alongside the replacement of cost of battery. It is also suitable for the economical calculation generated by Homer Pro, though there are some drawbacks since the PV power cannot be used at the night time in cloudy days, and still it is required to depend on diesel, especially in winter time, which increases the complexity because the power supply is very crucial in winter. Option 3 is the combination of existing diesel genset, PV panel and a battery storage. It is economically a good option with a low investment, but it falls back to satisfy the technical feasibility since in terms of less availability of solar radiation, it will store energy from the existing diesel generator. That will result in no additional savings in the project in the long run. This option is the combination, which is option 4, of diesel genset with battery storage and wind turbine. This will also have the same impact like the other options. So if we just analyze all of these options, we can clearly see that the option 1 probably is going to be the suitable one. Let's discuss in the next slide. This is the slide where we'll discuss the comparison of cost among these options. If we just break down the provided data, the net present cost, the levelized cost of energy and operating cost as well as the capital expenditure, we'll get a clearer picture. From option 1 we can see that the net present cost is 3.19 million. The total cost, which is the total cost over the project lifetime, the levelized cost of energy is 0.278 million. The cost per megawatt hour of electricity is 0.025 million per year, and the capital expenditure is almost 2.85. This option 1 is characterized by low overall cost in all categories, which we can clearly see in compared to other. So it is the suitable one for with a limited budget and lower electricity generation requirement. If we just take a look into option 2, we'll see that this option is significantly higher cost across all metrics, indicating a larger scale, high investment project. It might be suited for a large utility or industrial application with a substantial electricity generation and operational requirements. But the option 3, which is extraordinary high, which has extraordinary high net power cost and operating cost but a relatively low capex, this might indicate a project with a high operational demands and potentially high output for specialized applications. And option 4 has also a low overall cost but is slightly higher than option 1 in each category. So it might be suitable for similar applications as option 1, but since it's slightly higher than option 1, so option 1 may be the best suited option, best suited combination for our project. So if we just sum up, we can clearly say that option 1 is the best for our suitable best option for our project, since our main emphasis is to reduce the cost and we want to design a low cost microgrid. So and one of the main advantage is also that in terms of absence of PV power at night or cloudy days, battery can be utilized immediately. So it's a good backup option. There are some limitations in this project as well, since the project lifetime is 25 years, which is a long period. The several factors has been considered as constant, like the electricity demand, PV efficiency, battery efficiency, and the number of power outages. So in conclusion, we can say that our main goal is to reduce the electricity cost, which I've discussed earlier while I was discussing the options. The battery will only be used in terms of emergency, because we are planning a complete green energy. The project offers valuable insights into creating and evaluating small-scale hybrid microgrids, and it opens a new possibilities for utilizing the thermal heat and further developments in this renewable energy sources in this province. Thank you for your attention.